Nice pleasure. My name is Diego Pinto, and today I'm going to present physical versus computational modeling in hydraulics. Introduction: hydraulics as branch of engineering that studied the behavior of water and the of the fluids and recent or emotion requires analytic tools to predict behavior of real systems. In this context, to make my modeling approaches are suit physical modeling based on the construction of scaled down physical replicas of the phenomenon or infrastructure to be analyzed, computational or numerical modeling based on the mathematical solution of governing fluid flow equations using specialist software, such as this advanced limitation and specific application the show between or using combination depends on the problem to the solved available resource and required precision. Um, Physical modeling description. Physical modeling involves building scale models in hydraulic laboratories. These models replicate key features of hydraulic systems like canals, dams, spillways, rivers, and hydraulic structures. Advanced allows direct observation of flow behavior, ability to visualize complex phenomena such as turbulence, vortices, swirling, or score, ideal for validating innovative solution or in conventional structures. This advance, expensive in terms of time and money, requires specialist facilities and limited scalability. Not all phenomena can be accurately replicated at scale. Scaling in physical modeling, scaling is critical and is governed by similarity laws using dimensional numbers. For number preserved when gravity dominates the flow, and Reynolds number import to characterize laminar of turbulent flow, geometric, kinematic, and dynamic similarity fundamental to ensure model behavior represent to the prototype. This is often not possible to preserve a dimensional numbers simulated, so corrections for simplifications must be made. Computational model and description: this approach whose mathematical equation, Sylvenant equation for open channel for flow or navigating stocks for more complex flows to represent hydraulic systems. This solved numerically is using especially software. Advanced lower cost and time compared to physical models, and now simulation of multiple scenarios and sensitive analysis can be integrated real topographic data through GIS and satellite information. This advance requires advanced cooling of mathematical physics and programming, and results are highly dependent on input data quality and proper model calibration, and difficult to represent a highly localized of turbulent phenomenon with significant computation power. Software used in computational modeling, two-dimensional model, hierarchs, two-dimensional surface flow, hybrid open source, software developed by Spanish universities, My 21, two-dimensional simulator for water bodies, three-dimensional models, flow three-dimensional with used in complex hydraulic simulation, open source software for computational fluid dynamics, y ANSYS Fluid CFX community used in the industry for CFD simulation. Similarities between physical and computational modeling, both aim to represent hydraulic reality for analysis, design, or forecasting, but require calibration and validation with real-world data, but have inherent limitation and require engineering judgment. They can complement each other. Computational models of them reduce the number of physical tests and vice versa. Key difference feature for physical modeling and computational modeling. Um, First, represent time scaling, COGS, scenario flexibility, direct visualization, phenomenal reproduction, implementation time for physical modeling, Tahir replica en laboratory, y en computation modeling, mathematical simulation on computer, and scaling requires similarity laws y no required words at the real world scale in high material space implementations in relative low dependence on hardware and software scenario flexibility limited y computational modeling height direct visualization yes intuitive via graphics and post-processing and phenomena reproduction excellent for complex physical phenomena and computation and modeling dependence on model resolution and numerical setup implementation time physical modeling long computational modeling shorter in general. Hydraulic physical modeling laboratories. Hydraulic laboratories are equipped with adjusted slope channels and sedimentation tanks and model structures, data acquisition systems, camera, level sensors, velocimeters, instrumentation to measure pressure, flow rate, visibility, um, three-dimensional printing tools to manufacture scaled components. Example of major laboratories, National Hydraulic Laboratory de México, Hidroambiental de Colombia, Saint Anthony Falls Laboratory de Estados Unidos y CEGINAF de España. Common application. Physical modeling, design of speedwise dam and complex hydraulic structures, studies of score and local erosion, coastal and port models, verification of nonlinear behavior, y for computational modeling, fluid and overlap flow simulation, and use chunk assessments, prediction of sediment or pollen transport, y environment impact assessments. Conclusión. Physical and computational modeling are complementary tools. The current trend in hydraulic engineering favors hybrid models, where computational simulations support Preliminary design physical models validate key or innovate elements. The choice depends on project condition, require detail level and valued resource, but approach require specialist technical cons and in-depth understanding of hydraulic phenomenon. And thank you very much for your attention.